share my screen.
Yep.
Could you see the screen?
Yes, we can see your screen.
Okay. Hello everyone, my name is Xinyu Liu and I come from the team of Fuzhou University. First, we want to thank organizers of MagNet Challenge, which we think is a milestone activity for this field. And we would also like to thank other teams for their generous sharing of knowledge and insights. Next, we will introduce our work in this challenge. For the methodology, we use sequence-to-scalar transformer as the network structure. This network is modified from the transformer tutorial of MagNet GitHub. We remove the decoder and use a linear layer to regress the core loss. And two projectors are both composed of linear layers, where the projector B is used to embed the B curve, and the projector fusion is used to fuse three kinds of inputs. To train the network, we use a complex training pipeline based on transfer learning, which has three stages. In the pre-training, data from all 10 materials are used to train a general pre-trained model. This model is then employed in stage 1 fine-tuning to train a specific model for each material. In this stage, we obtain 10 models, that one model for one known material. In stage 2 fine-tuning, stage 1 models are used as pre-trained model to train model for 5 unseen materials, respectively. Finally, we obtain 10 models for each material, but only the best model for each material is retained. For the experiments, we train one model for one material. And, using the same network and training pipeline. MagNet data with 10 known materials are used for pre-training and fine-tuning. 90% of the given testing data are used to train the final model. The remaining is used as the validation stage. In data preprocessing, we use log transform for frequency and core loss. Then Z-score normalization is applied to all inputs and outputs. Note that we didn't do data augmentation. This is because we have a question that how does the ground truth change when the input changes? But based on the experience of other teams, data augmentation can bring good improvement. We think data augmentation is a very good topic. Here are our results. Test results and validation results are relatively close, except for material D and E. In particular, material D only has 500 samples and nearly has one excitation type for training. This is a very challenging situation since the distribution of training data and testing data is not always the same in the real world. We believe that the model generalization ability is an important research issue in this field. Next, we will introduce the discussions of the experiment. First, we found that there is a star material N87 in stage 2 fine-tuning. Pre-trained models from 10 known materials show varying effectiveness. An interesting observation is that N87 model achieves promising results among all test materials. We think that there may be some materials that represent the generic core loss modeling. Second, solving all problems with one foundational model is a current research goal in many domains such as CV and NLP. The results in transfer learning show that a better pre-trained model can achieve better performance. This suggests that there is some general knowledge in deep learning models that can be used for other new materials. This also provides a possible way to build a foundational model for colors modeling, which can be adapted to different materials without any adjustment, just like large language model GPT. Note that the foundational model doesn't mean the model size should be very, very large. It can also be a small one. Anyway, it's just an immature idea. The third is about the normalization, which has already been mentioned by many teams. The Z-score normalization is hard to use in small samples, and it is material-based that is inconvenient for both training and testing. We think a general parameter or a material-independent approach for normalization may be a solution. The first is the inconsistency of training, validation, and testing. There may be some factors to this inconsistency. The unexpected issues in data splitting. Maybe the model is tested on the training set. Mixed precision is not uniform, and the batch size is not uniform. A method in NumPy percentile is not the same. Next, we will introduce some attempts we have made. In the early stage of this challenge, we have tried to build additional datasets on our own. For deep learning, more data, more better. It's a natural idea to use extra data for better performance. Therefore, we construct a measurement system to obtain more samples. Here is our measuring environment. Here are our measurement settings. Finally, we get 662 samples for 3F4 material. Unfortunately, the result is worse, which has caused us to lose confidence in this solution and didn't use it at the end. We summarize some possible reasons for the degradation when using extra data. First, differences in measurement environments. Although we try to follow the environment of MagNet, due to the limited resources, it is difficult to achieve complete consistency. In particular, the frequency and excitation cannot be all-in with that of the MagNet data. We only have sine wave, which means we create a excitation challenge for ourselves. Second, difference in process and post-process of measured data. A standard publicly available guideline or cookie may be useful. Third, the samples are not enough, but measurement is time-consuming and labor costly for us. To measure one temperature setting, 2 students should use 3 afternoons. In the experiments, we use some tricks for model training. The first is that we use an efficient coding framework for deep learning called PyTorch Lighting. This highly speed up our research pipeline. We use Adam as the optimizer, but we didn't do comparison experiments to SGD. We use cyclic learning rate scheduler, which we found that it's better than OneUp. We use stochastic weight averaging SWA in the end of the training period. It is just like a model ensemble approach, and it works. We have tried using learning rate finder to find the optimal learning rate, but it is no better than a fixed learning rate. Furthermore, the changing learning rate makes it difficult to compare different modules, so we don't use it. We didn't use it. Also, we didn't use the optuna to fine-tune the hyperparameter because it is too time-consuming and the results are not always better. We use mixed precision to speed up training. It's very useful to save GPU memory, and we use gradient clip to prevent gradient explosion, but the effect is uncertain. We have tried using training longer times, but we found that using recurrent fine-tuning is better. Recurrent fine-tuning uses the trained model as pre-trained model for the next training period. We think there are two intuitive reasons here. First, the cyclic learning rate schedule ensures that the model does not always fall into a local optimum. Second, the stochastic weight averaging SWA is applied twice in the entire training period, which improves pre-trained model quality for later half training process. And we have tried fine-tuning from similar materials and found that pick the most similar material is better than pick multiple similar materials. Of course, from now on, the experiment on material D doesn't quite explain this problem, but we don't have more time at that time to do more experiments. This solution can be further attempted in the future. We have tried frozen layers, freeze some layers, usually shallow layers, in pre-trained model and fine-tune the rest is a common trick for deep learning application. However, this trick did not work well in our experiments. Perhaps the pre-trained model is not powerful enough. We project T and F before projector fusion in an attempt to allow the model to better mine knowledge of the missioning environment, but the performance gets worse. We also tried removing the word embedding of B curve. Let the encoder view the curve as a whole, and each point on the curve is a feature of that whole. Because we think 1024 points are enough to describe a curve, but it didn't work. We found an issue that is about the measurement error. The equation to obtain B curve assumes a uniform distribution of magnetic induction intensity within the core. However, the distribution of magnetic induction intensity varies at different positions. Under large excitation due to local saturation, the actual loss may exceed the computed value. However, we are not sure whether it will have an impact on measurement data and core loss modeling. We downsample the B curve from 1024 to 1 and find an interesting observation that even there is only 8 points in a B curve, the model can still get a good result. So there is a problem. How much valued information is contained in the B curve? Do we need so much features? This is a problem that we haven't figured out yet. This is the end of our presentation. Thank you for listening.
Wow, thank you, Xingyi, for the wonderful presentation. I would say your team's performance was great across the 5 materials, and you really did a great presentation covering a lot of very interesting concepts and ideas. So congratulations, this is wonderful.
Thank you.
Yeah, so I have a lot of things to mention. Let me try to remember. First of all, I like the approach of figuring out 1-star material. That's really good. N87, that's what we think could be a very feasible path in the future as well. Like identify a few representative materials for different frequency range and application range. And maybe always train a genetic model from that material. And then if there's a new material for those applications, you start from there. So this is a great try. And I like that. I personally like this approach a lot. I also like you guys playing with the measurement data. And that's why at the beginning of the competition, honestly, we don't know if our data is true or not. We try our best, but we don't know. I think the more teams try to set up the measurements, the more closer we will be to the truth. So really, this is a great attempt. And don't feel discouraged even if your data didn't match with us, because we don't know whether our data is better than yours or not. We tried our best. Then I think what else I have? I like your concept of MagNet GPT. That's our dream as well. I think it's all of us here. None of us can do it by a single hand. So that's why, as a community, that's maybe within 5 years or 10 years, we can have a MagNet GPT, which is a robot or is an expert, knows everything about magnetics, all the 100 materials, and knowing the behavior, the common behaviors among them, and the unique characteristic of each material. And then we just go and ask which I need to design a magnetic at a particular frequency for this particular excitation waveform at a particular temperature, which material is best. And then this ChatGPT will just give us the answer and give us, and even if in the future we can capture geometry influence or other influences, that can be a great advance in this field. So thanks for bringing this up.
Thank you.
Yep. Any other comments, questions? I guess this is a great chance we can discuss. There are so many interesting topics here.
Yes, so I saw there's really lot of good practice, and even some of this doesn't seem to work, but in the end, it's overall the performance of the model is really good. And which one do you think is the most important one that you use to improve the accuracy? Especially, you see you did pretty good in the material D compared to all of the other models, where I suppose probably is the transfer learning method technique that you use that really enhance the accuracy for all the testing material. But what are your thoughts? Which one do you think is most helpful?
I think for a more general pre-trained model may help. Maybe we can try to develop a new pre-training method using the self-supervised learning to build a more general pre-trained model for the material D, which has only hundreds samples. I think it may help.
I guess Haran's question is, what do you think is the best idea? Like you like the most among the many techniques you tried?
Maybe the whole fine tuning strategy, because
The strategy.
using this complex pipeline is because we don't want to waste our previous work. In the pretext, we train the general pre-trained model and train the pretext models. That's the stage one models. Thus, we don't need to do the pre-training and stage one fine-tuning during the final test because we already have these models. So we just directly use the pretext model we have to fine-tune. We also think this is the core idea of transfer learning, that we can reuse the work we have done before.
Okay, so you think the overall strategy, training, tuning strategy, and then how did you balance the model size and accuracy? What did you spend time, efforts in there? I noticed, I forgot. I thought your model was not.
We don't do the trade-off between the accuracy and the size. We just use the default setting. We don't fine-tune the hyperparameter, how much network, how much neurals, and we didn't do this.
Yeah, so you mentioned a few techniques. I like the floating point, 16 bits or versus 32 or even lower. I guess if we are targeting single-digit percentage error, then maybe we don't need 16 even. And I like the downsampling discussion you mentioned. So there are a lot of room for you guys to reduce the size of your model, looks like.
Yes, yes, yes.
Yes,
Okay.
yeah,
Wait,
just
go
a
ahead.
another quick one. Yeah, I'm also quite interested in you mentioned that the comparison between the using longer epochs versus doing the recurrent fine tuning. Could you explain a little bit more, like when you do the recurrent, what kind of techniques do you do? Like, what's the difference between this one and using longer epochs? For example, did you reset the learning rate or something like this?
No, we just keep the same. And the main difference is that the recurrent fine tuning use twice SWA, which provide a more better starting point for the next fine tuning process. We think this is the main reason for the recurrent fine tuning.
So in the end, you're trying to use the SWA to try to doing the average among multiple like sub optimal points so to get a. I see. Good. This is a good practice, I think. Yeah.
Great. Okay, if there are no other question, we'll move on to the next team. I believe it's TU Delft.
Hi, hello.
Hello.
I'll try to share the screen.